All right. So after punching 63.654 over 2 times 10 exponent 5, you're actually going to get 3.1827, okay, times 10 exponent negative 4. Okay, and it has no unit. And it has no unit. Exactly. Okay. So let's proceed. So this our answer over here. Finally, I can express this in this form. That is our strain. I told you the other day that this negative 4 you are seeing on top of this guy over here means that the 4 zeros came even before the values came. Okay, because it's a negative number. So that is 0.000. If that is, you want to write it in decimal, 1, 2, 3, 4. Okay. Uh-huh. 3, then the numbers will follow like that. 3, 1, 8, 2, 7. You see, then you can leave your answer like that because we said that it has no unit. It has no unit. Please, are we all getting the same answer? Are we all getting?
Yes, yes, please. Yeah.
All right, thank you. So, the last thing we are supposed to look for is our elongation. Okay, and what did we say elongation is called? Can anyone tell me what we said elongation can also be called?
Elongation. Elongation is change in length.
And what can it also be called? Hello,
Extension. Extension.
good. And what other thing?
Uh, I can't remember. Sorry.
In some cases, they can also ask you to calculate for the displacement of the. Okay. So take note,
Displacement.
take note of some
Okay.
elongation. This is the symbol for change in length. Okay. So at the end of the day, our change in length, that is, if we want to write our change in length, we have to put some formulas and then make one the subject from there to be able to find. But there are so many formulas, any one that you choose to. Let me show you something over here quickly before we go. That is, if you want to refer to this formula, it's that over here we said that E is equal to PL over what A times the change in length. You can make change in length the subject from this equation find for- to find for your change in length. Okay. Or you can also make the change in length your subject from what? This equation. This equation you are seeing over here. See. So whichever way you choose to adopt, just use it wisely and life is good. So let's use this one. I think this will be more simpler. Okay. So we know that. So let me start by saying that what strain is equal to, let me say, change in length, okay, over original length. Okay. Therefore, so this is just like a general rule. So from here I say that what therefore therefore we can now say that if E is equal to change in length over original length, then we can just do cross multiplication and then we get our change in length. So this is just like an asterisk. And finally, you realize that our change in length is going to be equal to what? Your strain times your strain times your original length. Any question? Any question before we proceed? Any question before we proceed? Okay, so this is the formula we have adopted for our change in length. So to get our change in length, finally we can just substitute the values into it, and life becomes easier. So our change in length, displacement, extension, or elongation is now equal to the strain. What is the answer we had for the strain? We had 3.1827 times -4, okay, times the length 1000 what 500. So you see that we are calculating for the strain in the material, 1500 millimeters. Okay, so it is just because of this guy, that is why even change in length is having the unit. If not, that change in length may have not also had a unit. Okay, strain has no unit. So once it's going to multiply someone with a unit, it's just adopt that unit. Good. So let's quickly multiply this together and let's see the answer we're going to get. What are you going to get? After multiplying, which answer did you get? I'm getting 0.47745. Okay. Millimeters. Millimeters. So I think we are done solving question one. We are done solving problem one. Any question, any challenges, any contribution before we continue to pick questions from wherever we began to wherever we have gotten to. Please, anyone have anything to ask before we proceed? All right. So let's come to our question. Okay. So let's come to our question two. Question two, can anyone read the question for me? And let's quickly analyze this question together. Okay. So the question says that problem 1.2. One because we are in lecture 1.2 means this is example 2 of lecture 1. Determine the maximum shear stress in the rivets in the cases, okay, shown below. Case 1, P is equal to 25 kilo Newton and the diameter of the rivet is equal to what? 20 millimeters. In case 2, the force is 35 kilonewton and the diameter of the rivets are 16. Yes, okay. So this is for case 1. As you can see, this is for case 2. In case 1, how many diameters do we have? Realize that at the end of the day, we are going to have just 1. Okay. But in case 2, you realize that we have 1 diameter at this side. We also have 1 at this side. Okay. So it should tell you that even if you are calculating for your area, the area will be multiplied by 2. Okay. But over here is just 1. So if you just do for 1. Good. Anybody to read the question for us one last more time before we begin?
Determine the maximum shear stress in the rivets in the cases shown below. Case 1, P is equal to, P is force, right? Is equal to, hold on a minute, 25 kilonewton, and the diameter of the rivet is equal to 20 millimeters. And B, case 2, P is equal to 35 kilonewton, and the diameter of the rivet is equal to 16 millimeters. In the diagram below.
Okay. So because at the end of the day, see that this is the area resisting shear. You see what they're fitting over here. This is the area that is. So because of that, it means that the force that this guy is actually a shear force. Uh-huh. The question is after determining the maximum shear stress below. Okay. So we are supposed to determine the shear stress in case 1, and also we can also determine the shear stress in case 2. That is all we are just going to do. So let's quickly put down our given and then we move faster. So let's assume we are done analyzing the question. Okay. Because of the time, we'll have to move a little bit faster. Once you understand certain concept, then I think I can accelerate with other ones. Yes. So this is our problem 2. So let me write over here 2, no, 1.2. 1.2. So this becomes our given. The given is very important because it's also going to attract very, very much more mark. Okay. So the case 1, this is our case 1. That is a single shear. Okay. Because you can see, as you can see in the question, it's just 1 over here. Okay. So it's just it's just going to undergo a single shear. And we also have a case 2. So let me put case 2 over here. Good. So this is a single shear. This is a single shear. So the shear force acting over there. If this is a single shear, what do you think this is going to be in the case 2? Double shear.
Double shear.
Double shear.
All right. So the shear force E, the shear force is equal to E, which was given in the question. So let's go and see what the shear force was. And the shear force was equal to P, which is equal to 25 kilonewton, and the diameter was 20 millimeters. So let's quickly express this, and that is going to be what? 25 times 10 exponent 3. So they said 25 kilonewton, which is equal to just 25 times 10 exponent 3 Newton. Good. And then the diameter is equal to D, which is equal to, let's say, 20 millimeters. It was given in the question. Okay. So if I can quickly pull down the diagram over here, I'll be glad. Let me see if I can do that. So you see the thing is of a form of something like this. And also we have this moving part. Okay. Okay. So that is the area resistance shear. That is the area resistance shear and the force acting on this, as you can see, which is limited as our P. Let me quickly use a different color pen to do that. So right over here, P, right over here. So this is the area resistance here. So area resistance here. Area resistance here. Good, good. So let's also look at the second scenario, and I believe life is going to be much more easier. So the shear force was 35 kilonewton. That is the shear force, 35 kilonewton. Shear force is equal to 35 kilonewton. And this same 35 kilonewton is the same as our what? P, which is also the same as what? 35 times 10 exponent 3. I told you that if you say A is equal to B, then it means that also B is equal to what? A. That is the meaning of that. Good. The last but not the least, the diameter. So we say that the diameter of rivets diameter of rivets, comma D is equal to 16 millimeters. Okay, remember that there are two. Okay. Mhm. So let me put a drawing over there so that at the end of the day we don't get confused. So these are the you can see that over here we have just one rivet. Okay, so this is a rivet. This is the rivet. Let me use a different color pen to denote that. Okay. So in this scenario, we have two rods this way. This one is acted upon by a force. Also, this also acted upon by a force P. So you see, at the end of the day, we have something like this. Please remember to do all of these things. So don't say it's not important to. You'll be awarded marks for all of this. If you fail to do it, you lose marks. I could have skipped it, okay, and say, oh, let's go and solve the question quick, 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 and let's go. But once I do that, some of you will begin to practice that and you realize that it's going to be like I'm teaching you a wrong thing. Okay. So I have to do the right thing for you to see. So that at the end of the day, if you also go and you are working in the examination hall or for future purposes, you also do the same thing. After that is going to serve as a guide to you as you are solving your question. If you fail to do this, you will struggle yourself in your calculations. Okay. So in this case, you see that the rivets are two. In this case, you see that the rivets are two. Good. Okay. So let's proceed. So this one, the area resistance shear are these places. And let me say these places. Okay. So take note of them. That is the area dot resisting dot shear. So don't get confused with that. Let me quickly so that you see it well. And then also these are the rivets. You see that over here, two rivets have been placed over there. So let me call them the rivets. Okay. So what else? Let's quickly solve our work and then let's proceed. So we have case one and also have case two. Okay. So they say we should calculate for the maximum shear stress rivets in the cases below. Okay. So let's just go to the solution and life becomes easy. So this is the solution. Uh-huh. So we just want to pick case one and calculate for its share. Later we pick case two, we calculate for its share. So let's say this is the case one. Okay. So this is the case one. So we are calculating for share in case one. As simple as that. So the shear force, in this case, we are calculating for the maximum shear stress. Okay. Mm. In this case, we are calculating for what? Hello? We are supposed to calculate for
Uh,
maximum shear stress, right? So I can write stress over here with maximum over there. That is the maximum shear stress. Okay. But take note that it's true that I'm calculating for maximum stress, but the word shear that is added to it, it brings about a concept. Okay. That brings about a concept where I'm going to take you back to the slides now for you to see it for yourself, so that in future it doesn't affect you. Okay. So our shear stress over here is what we don't know. So the shear stress question mark. So that is what we are supposed to look for. Take note that the shear stress in this case can also be denoted as, we have stress, but we have what? Normal. We have so many types of stresses. I'll be taking you over there now and you will see it. Okay.
Compressive, normal, and then shear.
So the types of stresses, can we all see types of stresses? So you see, these are in general, these are the what types of stresses. Okay. So we have the normal stresses, which I told you, that is the tensile and then the compressive. You see that they've,
Compressive,
and we have longitudinal stress. We have the Hooke's or circumferential stress. We also have the tangential or shear stress. And this is the one they asked us to calculate for in the question that we are in now. You see, so the shear or tangential stress, it has a symbol. It has a symbol. You see that for the normal stresses, they are using this symbol over here. And what is the name of the symbol? It is called what? Sigma. Can you see? This symbol is called what? Sigma. Okay, good. But in case of shear stress, how are we going to call it? Look at, they say shear or tangential stress. In this case, the name is what? Tau. So for tangential stress, the name we are going to be using is what? Tau. Okay, so you see in this case, instead of you writing what? Sigma is equal to what? Force over area. We are rather going to be writing what? The tau is equal to what? Force over area. Okay. Uh-huh. So because I don't want you to get confused at the end of the day. So let's quickly go back to where we were and then let's proceed. Yeah. Okay. So this over here, we said that we can also use the symbol known as tau. We can also use the symbol known as tau. Okay. So this, we can use this symbol over here, which is what? Unknown. So if we want to look for it, we can now say that our tau is also equal to force over what? Area. P over A. Okay. The force was given to us in the question. What was the value of our force? In the first one, 25 kilonewton. So 25 times 10 exponent 3. So that is 25 times 10 exponent 3 Newton. The area is unknown. But in this case, I told you the one we are going to be adopted because it is D we were given. We are not given radius. So why do you go and use a radius formula? Come and see the three formulas for the area I gave you over here. Take very clear look at them. The first one is that it has diameter in it. The second one, it has radius. This one has T. If we were given diameter, why don't you use just the diameter one and move straight and go? Don't make life difficult for yourself. If you still want to use this formula, it means that you have to come and divide the diameter by what? 2 to get the what? Radius. And that is a very long step. Don't play with that. Just use this one straightforward. Pi d squared over 4 and life becomes much more easier. Okay. So this is where we are. And then this can be found for using a formula of, so we said that now our A is equal to But our A is equal to what? Pi d squared all over 4. Okay.
4.
Finally, we can say that what? Our pi, we are adopting 3.142 times what? What is the diameter of the first rivet? The diameter was actually 20 millimeters, right? So we put 20 millimeters in the bracket. So 20 millimeters all squared. So someone should quickly point this for me. Let's get the area so that we can accelerate. Let's quickly do this together. 3.142 times 20 squared. Okay, all over 4. And you realize they are going to get 314 points.
314.2.
So that is 314.2 millimeter squared. If you mention an answer without a unit, you'll be marked wrong. I told you in our previous lectures. Good. So we can just now substitute this into our equation and life becomes much more easier. So our tau, in this case, can be written as what? Our force is 25 kilonewton. So that is 25 times 10 exponent 3. The kilo means 10 exponent 3. Okay. Newton all over 314 millimeter squared. Failure to add unit to your answer will cause you to be penalized. So please let's all do what to always add our unit to our work. So finally, we can say that our tau is equal to, let's quickly point this together. Let's say 25 times 10 exponent 3. Quickly, all over 314.2. And you realize that we're going to get 79.567154 force. It continues that way, but let's just maintain our answer in 4 decimal places. The more your decimal places, the more accurate your answer become. Take note. So 79.56
56.715.
7. So let's just maintain 4 decimal places. So it becomes 7.2. Okay. Now we can bring the units.
Okay.
In this case, I will not write this way. I want to write in a more modernized way. So I'm going to write Newton per millimeter squared. So we are done with case 1. Case 1, that is the answer we had. We can quickly solve for case 2 too, and life becomes more easier. Can we proceed to solve for case 2? You can see we are done solving for case 1. Any question on case 1 before we proceed? Any question on case 1 before we proceed? Please, do anyone have any question to ask on case 1 before we proceed?
Please. The final answer you got is 79 points. It's supposed to be 79. Oh, I got it wrong. 7956.71 or 7956.7, yeah, or 70.
Point can only come once, okay? A decimal point can only come once. When
Uh, okay. The next value after the 1 is 5. So you run it up to become 2.
Thank you very much. That is what I actually did. If it is 5 or more, you can run. Assuming it was 4, I can't run. I'll just maintain it like that.
Okay.
So can we proceed? Okay. So in 10-minute time, the link is going to go off, but I wish we can just complete this so that tomorrow we see how best we can proceed with lecture 2. For the rest of the examples, try to play with them on your leisure time, and life is going to be much more easy. Anyway, is there any difficulties anyone wish I could clarify? So this becomes the case 2. So we are now solving for case 2. So we just have 10 minutes to go. And in the case 2, we are supposed to calculate for the maximum, or let me say the shear stress, right? Yes. So shear stress, and this in this case is a double shear. Okay, so let me just write the double shear stress. So okay, let's say we are asked to calculate for the shear stress. So the shear stress is unknown. Okay, the shear stress is unknown. It's unknown. So if you want to look for that, first of all, we have to be able to know the formula for that. And the formula for this shear stress, this is the symbol for shear, and that is the same P over A. Okay, good. But the P was given to us as what was the value for the P? Let's go back to the question. Um, let's quickly go back to the question. The P was 35 kilonewton, and the diameter is 16. So this is 35 kilonewton. So 35 times 10 exponent 3 Newton. All over the area is unknown in this case. It's because we have to calculate for a different area. Case 2, a different drawing was produced. You see that this case 2 has a different drawing. Because of that, we have to calculate for a different area. We can't use the formula for the first area. Good. Due to that, we are saying that our A, which is the area, is now going to be equal to what? We know that our A is equal to pi d squared. Okay, all over 4. But in this case, because that the rivets are 2, look at the drawing we did. The rivets, because there are 2, you see that there are 2 rivets. So we say that 2 hot rivets. Okay, this is a key point. Keep it very well. There are 2 rivets, and because the rivets are 2, we have to multiply the area times what? 2. Okay, so we are going to say 2 times what? Whatever we are going to do in this bracket. Good. And we are doing that because rivet is 2. So the pi we are using is 3.142, 3.142. Okay, times the D. And the D is 16 millimeters, all squared, all over 4. So someone should quickly tell me the answer. So what is the formula for our A? What is the formula for our A? Okay. If no one is mentioning the answer, let me do that by myself. 3.142 times what? 16, all squared, all over 4. We are going to get 201.008. Okay, but since the diameter, the rivets are 2, we said that we multiply this by what? 2. So if you put all of that into brackets and you multiply it by 2, you realize that we are going to be getting 402. Okay, 402.
02.176.
Shame on you all. Shame on you all. Where were you when I was looking for you? All right, I have to finish punching before I start hearing answers, and that was quite challenging for me. Okay, so 201.088. If you continue to multiply this by the 2, finally you are going to get what we were getting. Okay, so that is, you are now going to get 402.176 millimeters squared. Okay, yes. So to make, so this is millimeters squared. Good. Let's quickly substitute this into our equation. We have just 5 minutes to go. So we said our maximum stress, our shear stress is now going to be equal to the load that was given to us. 5 kilonewton. That is 35,
Yes,
35 kilonewton. So 35 times 10 exponent 3
exactly.
Newton all over 4017
4.2.172
millimeters squared.
square.
Yes. So finally, what's going to be the answer? Let's all do that together. 35 times 10 exponent 3, all divided by 402.176. So we're going to get 87.0.
0266.
7.
I said, what did I say we'll be doing initially? You want to maintain 4 decimal places.
What decimal places? So 66. 87.0266 millimeter square. Newton per millimeter square.
So that is Newton
Yes.
per meter squared. So if I leave my answer in 4 decimal places and you leave your answer in 6 decimal places, who do you think is going to get a full mark? Or who do you think is going to be more precise?
Yours.
It is actually the one who left his answer in 6 decimal places that is going to be more precise. You understand me? The more your decimal places, the more accurate your answer.
Okay.
So on this, I continue to say that the laws of physics are the same for all observers in uniform motion relative to one another. I'll urge each and every one of us to know the Hooke's law very well and to be able to what? Express it mathematically. Okay? And you should be able to derive all the formulas from the what? Hooke's law. That is what is going to help as the basis. So, but for the rest, with time, they will come naturally. If you really understand the Hooke's law, you're able to state it, even you're able to tell someone that if a material is loaded within an elastic limit, stress is directly proportional to strain that produced by the stress. At least the person is what? A little bit uh, learned. Do you understand me? Also, you continue to tell the person that the proportional sign over there, it is actually directly proportional. That means that once stress is increasing, strain is also what? Increasing. To eliminate the proportional sign, we have to introduce a what? A constant. Okay, that is K, which is also going to bring an equal to. Take note that the K in this case, okay, is going to be equal to what? E for normal what? Stresses. Okay, now we have our relation that stress is equal to what? Elasticity times the strain. From that, you can derive all other formulas. Okay, please, I'll urge each and every one of us to take the basics serious. Okay, if your bases are weak, the exchange rate will always what? Expose you. That is, if the fundamentals are weak, the exchange will always what? Expose you. So
Quoted.
I beg you all, try and take your time, okay, and understand the basis. These are the bases that I'm giving to you, the basis to strength of material. If your bases are not good, you can even go and be learning lecture 10, 7, 8, you will still not, you will struggle, okay? But if you realize, if you really understand the basis, you can even pick a slide that you have not been taught and you realize that the understanding is going to flow naturally. Because why am I saying that? Once you apply the laws of physics, which we are saying that they are the same for all observers in uniform motion relative to one another, it is always going to work. You understand me? Always remember to work with your units so that if you are doing something wrong, you will know. Okay? If you are doing something wrong, you will know. Always work with the unit. So thank you very much for your time. May God richly bless you all. I really had a wonderful time with you all. Bye bye.